Our EMG circuit went through different evolutions. This is our first implementation of it. And version 2 is pretty much the same thing as version 1, but it's just a cleaner version. The big difference between version 2 and 3 is we decided to use the INA 2128. We initially used a different op amp, a one channel, the 128 up here. But when we were testing different muscles, there was a lot of crosstalk that was occurring. And we also wanted to expand our design to include more than one muscle group. And lastly, we have a PCB design of this board right here. Now, our result of the two-channel EMG circuit, we had an output range of 0.5 to 2.5 when the muscle was contracted. And we had a gain of 820. And these are two of the muscles, the tibialis anterior, which would be right out here. Oh, sorry, right in here, your inner shin, and your lateral gastroc, which is your outer calf muscle. And now I'm going to explain more about this.
Thank you, Noor. Well, accelerometer measures acceleration, obviously, but there's different parameters for accelerometers. You could choose a digital or analog accelerometer. In our case, we chose analog accelerometer because we could determine the sampling frequency we wanted from using our microcontroller. There's different number of axes. We went with the 3 axes, the X, Y, and Z coordinate, just because we implemented the accelerometer in the shin guard, so the leg is moving 3 dimensions, moving forward, back, up, down. It can move in any directions, especially the soccer player during the kick. The maximum swing determines acceleration, is measured in G's. For our purposes, our accelerometer range from 3 to 5 G's, just because higher G's are needed during fast running and kicking. Bandwidth, that pertains to digital accelerometers, and that's basically your sampling rates. What we decided to use was this particular accelerometer, is because it had an integrated voltage regulator with it, which we later used. We used the output of that voltage regulator to power our microcontroller. We're talking about microcontrollers. It's an essential component to our system. It acquired the signal and transmits it wirelessly to a PC. Our final testing, our transmission range was about 15 to 20 yards. But we particularly chose the MSP430. There's several reasons why. There's low power consumption. It uses about 9 microamps when it's low power mode. And the way we configure the microcontroller, it's usually low power mode when it wakes up and samples at 1,000 hertz. We use a 10-bit ADC. It provides a better resolution compared to the 8-bit ADCs that are out there. The MSP430 provides a clock frequency of up to 60 megahertz. For our particular case, we use 8 megahertz because it provides better power, less power consumption, and we didn't need something that fast. The target board. Luckily for us, the TI makes a very neat target board. You can see it in red here. You can see what it is. It's a 1-inch squared device. It has a microcontroller, a CC2500 RF transceiver, and a chip antenna. It's a pretty small device, and it's easily implemented into the shin guard, into the rest of the circuitry. So we didn't have to worry about designing an RF antenna or going into how do you interface a CC2500. That was the main focus of our project. The RF transceiver CC2500, one of the great advantages of that is that it has a transfer rate of up to 500 kilobits per second. One of the advantages of that is that you're allowed to sample more channels or more signals. So if we wanted to sample another muscle or sample a higher frequency, the RF transceiver can handle for the data transfer. There will also be another receiver. There'll be an RF microcontroller interface at at the shin guard, and there will be one at the receiver end on the computer. On the graph below, what we see here is using this spike controller, we acquire this EMG signal. And so the spikes is a contraction of the tibialis anterior, and then release and the contraction, and then we do this periodically, and we plot it output in MATLAB.
Now this was our budget. So grand total would be at $442.68, and our total labor hours came out to be, with billing costs, it was at roughly $15,000 for this project. And now we're going to show you a short video of our, we were planning to show it here, but it's really small and didn't really work out perfectly.
Hi, so this is a demo of our EMG implementation along with our force sensor implementation. We have Noor hooked up here. We learn tibialis anterior ankles as well as their lateral gastrocnemius muscle. They're above the shin and calf regions, as well as reference electric. We've all gone into the instrumentation amplifier and the filtering and conditioning stages of the data acquisition circuit. And we also have the force sensor hooked up. If you can zoom in on the oscilloscope output there. Noor, do you want to flex your shins? The flexing. So that is the interlock sheet data to the other sensors. And from the same sensor, I'm going to stomp on this or just press down lightly on this force sensor. And we're getting activity on the top signal from the force sensor and the bottom signal from the EMG channel.
Okay, so basically what we designed is a multi-channel signal acquisition device that could be used to analyze the signal. In our case, we use a soccer player, coach, trainer, we use the signal acquired to monitor the player's state, physical state. This wireless system could be implemented or could have other applications. It could be used during conditioning or during training or rehab, and it could be applied at other muscles or other sports. So a football player wouldn't necessarily worry about the lower extremity, or maybe a high extremity, maybe a quarterback. So the system is, we designed it so it will be small, lightweight. We have certain constraint, lightweight, small, portable, and low power consumption. Lessons learned. PCB fabrication. We try to make our own PCB. It's very labor intensive. I wouldn't recommend it to anyone. Just order the PCB and get it over with. Limited research period. We spent a lot of time, I think, especially for a 9-month project, researching EMG signals and researching force and how to, most EMG signals and most amplifiers work at 9-volt input, require 9-volt input, and we try to reduce it. We got it down